In this video, we're going to talk about what a singular value decomposition is. So I mostly want to motivate what it is. So we know that if A is an n by n symmetric matrix, we can orthogonally diagonalize it. So we can write it in the form A equals P times D times P transpose, where D is a diagonal matrix and P is an orthogonal matrix. So D is a diagonal matrix and P is an orthogonal matrix. So one of the reasons why this is useful is because of a property that orthogonal matrices have. So I want to state a cool fact about orthogonal matrices. It turns out that orthogonal matrices are either rotations, they're matrices that perform rotations, or reflections, so if you reflect across a line, or combinations of the two. So for example, here is one orthogonal matrix. So I'll do 1 root 2, 1 over root 2, and the next column will be negative 1 over root 2, and 1 over root 2. So this is a square matrix, and the columns are orthonormal, so this is an orthogonal matrix. And it turns out that this matrix rotates vectors pi over 4 radians counterclockwise. So if we wanted to, we could derive that fact directly. We could think about this transformation, the transformation that rotates vectors pi over 4 radians counterclockwise about the origin, and find its standard matrix. And if we were to find its standard matrix, it's this matrix that I've just given right here. So this was an example of an orthogonal matrix, and it is, in this case, a rotation matrix. All right, so this is useful because this breaks down problems that involve a matrix A. So maybe I should say a symmetric matrix A. So involving a symmetric matrix A into the pieces that A is sort of decomposed into. So it's decomposed into P transpose times D and then times P, but in the reverse order. So both P transpose and P are orthogonal matrices. So both of those are either rotations or reflections or combinations of the two. And then D, the diagonal matrix, what that does is it scales vectors. It'll either stretch them or shorten them. So when we have a symmetric matrix, this is nice. It's useful sometimes to be able to think about what that matrix is doing in terms of these pieces. So the problem, though, in general, is the following. So I want to state what the problem is in general now. So very few matrices are symmetric. So ideally, we want a way of doing something similar, so decomposing A into a nice form like this, doing something similar for non-symmetric, arbitrary matrices. Okay, so I'm going to underline the word non-symmetric. So the process that we'll use to do this is what's called a singular value decomposition. So the singular value decomposition will apply even when our matrix is not symmetric. In fact, even when it's not square, even when A is just an m by n arbitrary matrix, we're going to be able to write it in the form U times sigma times V transpose, where U and V are both orthogonal matrices, but U is an M by M orthogonal matrix. So the M here matches up with how many rows A has. And V is an N by N orthogonal matrix. So the N matches up with how many columns A has. And the sigma in the middle is going to be an M by N matrix, so the exact same size as A, but it's going to be something that's kind of close to a diagonal matrix. The only elements in this matrix that are allowed to be non-zero have to be along the main diagonal. Anything that's not along the main diagonal is going to be 0. But it's not a diagonal matrix necessarily because it's not a square matrix in general. It's M by N. So in the next video, we will start to talk about what do U, sigma, and V look like.